All right, so let's expand on the activity from class a little bit. We know that the derivative measures rate of change of a function, right? And that's the same thing as slope. The derivative is just a function that tells us the slope at any point of our original function. We can use this idea then to study motion of objects moving vertically, like tossing a ball up in the air, or horizontally, like a vehicle moving back and forth along a straight road. Generally, though, we can just think about a particle moving back and forth across the x-axis, where we're measuring the distance from the origin. So we can say that the function s of t, right? So s we're going to denote as our position function, gives the position of an object relative to the origin as a function of time. T stands for time. So we looked at position graphs in the activity, and we looked at some of the vocabulary as well. Right? So the rate of change, or the derivative of position, is velocity. So symbolically, we can say s prime of t equals v of t. The derivative of position is equal to velocity. Now, velocity, remember, does have, or is dependent on direction. Okay, so we can say if velocity is positive, right, and we're talking about something moving back and forth horizontally, right, like a particle moving back and forth across the x-axis. If velocity is positive, that means our object is moving to the right. If velocity is negative, that means we are moving to the left. And if velocity is equal to 0, that means we are not moving at all. Right? That means that we are stopped. Similarly, if we're talking about something moving in a vertical direction, if velocity is positive, we can say that we are moving up. If velocity is negative, we can say we are moving down. And again, if velocity is equal to 0, we are not moving at all. We are stopped. Right? Now, all three of these ideas will be important, but this is kind of a key one. There will be a lot of questions asked about where is the particle stopped, or where is the particle not moving, where is the velocity 0. Those will be common questions. The derivative of velocity, then, is acceleration. So symbolically, we can say the second derivative of position is equal to the derivative of velocity, and that is equal to acceleration. All right. Now, in terms of where acceleration is positive, acceleration is negative, and acceleration is 0, these are a little bit trickier to visualize. Okay, so if we're thinking about something moving, left and right, if acceleration is positive, what that means is it's being pushed to the right. Right? If acceleration is negative, it is being pushed to the left. Now, that doesn't necessarily mean that if acceleration is positive, it's moving to the right. It could be moving to the left, but the force that's acting on it is pushing it to the right. Right? Similarly here, right? Being pushed to the left doesn't mean it's moving to the left. Right? That just means that the force that's acting on it is trying to push it to the left. Then if acceleration is 0, that doesn't mean that the particle is stopped. That just means that it is not speeding up or slowing down. So this means that we would be moving at a constant velocity. Right? Velocity remains the same. So similarly, if we have a particle moving up or down, if acceleration is positive, we can say it is being pushed upward If acceleration is negative, that is being pushed downward. And if acceleration is 0, again, we have a constant velocity. All right, now, position, velocity, and acceleration are the three big ones that we're going to look at. But it's interesting to note that there are actually a bunch more named derivatives when we talk about particle motion. The derivative of acceleration, okay, is actually called jerk. Right? This one you might see a little bit. Right? So symbolically, this is saying the third derivative of position is equal, is equal to the second derivative of velocity, which is the derivative of acceleration, which is jerk. Now, these ones, the fourth, fifth, and sixth derivatives of position. Right? So the fourth derivative would be the derivative of jerk. This is actually called snap. The fifth derivative of position is crackle. And the sixth derivative of position is pop. I'm not making this up, right? The fourth, fifth, and sixth derivatives of position are snap, crackle, and pop. Right? I do not know which came first, these names or the Rice Krispies slogan, right? But this is for real. The third derivative is jerk, fourth is snap, fifth is crackle, and sixth is pop. You'll probably never see that again, but it's just a little interesting tidbit. All right, so let's jump into a problem and try to look at this a little bit analytically. So let's say that we've got this function, right, and this is the position of some particle. So first, we just want to find the velocity and acceleration functions. Well, that means I want to take the derivative of position. Right? Velocity is the derivative of position. So velocity is s prime of t. So I'll write all these out here. S prime equals v. So my derivative, let's see, 3 times 1/3 is 1. So I just get t squared minus 8t plus 7. Then my acceleration function is the second derivative of position, first derivative of velocity. So the derivative of my velocity function would just be 2t minus 8. Okay, so we have our velocity and acceleration functions. Now let's ask a few more questions about those. So this is a classic one. Okay, find all times when the particle is at rest. Right? At rest or stopped. There's even a couple other ways that this may be worded that we'll look at later. Okay, but what we want to do, okay, whenever we see at rest or stopped, what that tells me to do is set my velocity function equal to 0. Okay, so my velocity function was t squared minus 8t plus 7. So I'm going to set t squared minus 8t plus 7 equal to 0 and solve. So this is a quadratic. First thing we want to check is to see if it factors. So we want two numbers that multiply to positive 7 that add to negative 8. So I think negative 7 and negative 1 make this factor nicely. So setting both of these equal to 0, we would get t equals 7 and t equals 1. So there are two instances when this particle is at rest, after 1 second and after 7 seconds. Right? So next, we want to find the position and acceleration when the particle is stopped. Okay, so well, we just found two instances where this is true. Right? The particle is stopped at t equals 1 and t equals 7. So if I want to find the position and acceleration, all I'm going to do is plug 1 and 7 into position and acceleration. So I want to evaluate s of 1, s of 7, and a of 1 and a of 7. So if we plug 1 into my position function, I won't bore you with the calculations. I think we just get 19/3. And if I plug 7 into my position function, I think we get negative 89/3. Okay, so this is saying after 1 second, the particle is about 6.33 units to the right of the origin, but after 7 seconds, it's almost negative 30 units to the left of the origin. Okay, that's what these two things are saying. Then acceleration, if I plug 1 into my acceleration function, what do we have? My acceleration function was 2t minus 8. So 2 times 1 is 2 minus 8 is negative 6. And if I plug 7 into that, 2 times 7 is 14 minus 8 is positive 6. All right. So let's take a look at E. So E and F, okay, say find the velocity and acceleration at 2. Okay, so that means I want to plug 2 into my velocity function and plug 2 into my acceleration function. So my velocity function, t squared minus 8t plus 7. So 2 squared minus 8 times 2 plus 7 is 4 minus 16 plus 7 is negative 5. And acceleration is 2 times 2 minus 8, so negative 4. So, is the particle moving left, right, or stopped at t equals 2? Well, if our velocity is negative, velocity being negative, we go all the way back to this chart. Whenever my velocity is negative, that means I'm moving to the left. So, since v of 2 is negative 5, I'm moving to the left. We are actually going to skip h for now on this. That's something we're going to talk about tomorrow. All right, so I want you guys to go through and try this one here. Okay, our position function is t times the natural log of t. All right, so go ahead, take a minute, and try to find our velocity function and our acceleration function. All right, so velocity is the derivative of position. So s prime of t is velocity. And this is a product of two functions, so I have to use product rule here. So derivative of the first is just 1 times the second, so 1 times natural log of t, plus the first times the derivative of the second. So derivative of natural log of t is derivative of the inside over the inside. So we can simplify this quite a bit before I take my second derivative. This will just be natural log of t, and then t times 1 over t would be t over t, which is just 1. So now, if I want to take my derivative, that's s double prime of t, which would be v prime of t, and we don't have to write this out every time. Okay, I'm just going to write it out in the beginning stages of this lesson so that we hammer home that acceleration is the derivative of velocity and velocity is the derivative of position. So now, to take this derivative, well, again, derivative of natural log of t would just be 1 over t, and then the derivative of 1 is 0. So my acceleration function is just 1 over t. Right? So now, with that, you guys take a minute to find all times when the particle is at rest. All right, so when the particle is at rest, we want to take our velocity function, remember, and set that equal to 0. So my velocity function is natural log of t plus 1. So I'm going to say natural log of t plus 1 equals 0. Well, I need to get the natural log function by itself, so I'll go ahead and subtract 1 from both sides. So we get natural log of t equals negative 1. Now, to get t outside of the natural log, what we do, remember, is raise both sides to be a power of whatever the base is. So the base is e. So I'm going to raise both sides to a power with a base of e. So e to the natural log of t, that cancels out, and all we're left with then is t over here, and then over here we have e to the negative first power, or we could just write that as 1 over e to the positive first power. Right, so this is my only time when the particle is at rest. Right? Excuse me. At t equals 1 over e. All right, so you guys take a minute and try D here. All right, so find the position and acceleration when the particle is stopped. So what I want to do is plug 1 over e. Actually, let's write it as e to the negative first. I want to plug e to the negative first into my position, and e to the negative first into my acceleration. So position was t times the natural log of t, and my acceleration was just 1 over t. So I can simplify these quite a bit, right? The natural log of e cancels out, right? So the natural log of e to the negative first would actually just be negative 1. So this, and I can write this as 1 over e. This would be negative 1 over e. And 1 over e to the negative first, well, I can actually just bring this up to the numerator and change the exponent to a positive 1, right? So 1 over e to the negative first is just e, right? So you guys take a second, try to find the velocity and acceleration at t equals 2. All right, so velocity function was natural log of t plus 1. So natural log of 2 plus 1, and we can't really do any simplification from that. I mean, we could put that into the calculator and get a decimal, but we can just leave it like that to have an exact value. And the acceleration, so a of 2, was 1 over t, so that's just 1/2. All right. So to finish this out, is the particle moving left, right, or stopped at t equals 2? Well, what we want to look at is the velocity positive, negative, or 0? Well, this is a positive value, right? I don't know exactly what natural log of 2 is, but I know it's positive. So natural log of 2 plus 1 is a positive value. That means that the particle is moving to the right. And again, we'll take a look at h tomorrow when we look at speed. All right? So I did want to look at one other thing here. Right? So let's actually go back to the first example and look at this function. Okay, this is my position function. We said it was 1/3 x cubed minus 4x squared plus 7x plus 3. And I chopped it off just to start at 0, right, because we don't usually talk about negative time. Right? This is the t-axis in this case. So I'm starting at t equals 0, and then this is what the position of my function looks like. So what we found was at 1 second and at 7 seconds, the particle had a 0 velocity. Right? So right here, we can actually see the slope of this graph is equal to 0. Okay? We know that that velocity is the slope of position. So the slope at these 2 points of my position graph is equal to 0. Right? If we take a look, so I can turn on my derivative, this was what we found the derivative to be, right? X squared minus 8x plus 7. At those values, at 1, my derivative crosses the x-axis, and at 7, my derivative crosses the x-axis. Right? That's what we solved for. We solved for where the derivative equaled 0. So that told me here on the position graph, the derivative was equal to 0. Right? We're going to look at a lot more graphs tomorrow. We're going to dive a lot deeper into that part. Okay? But today, the big idea was looking at some of this analytical stuff. All right. So again, we'll look at more graphs tomorrow.